The first quiz problem for today involved a situation where the rate of temperature change for some object, say a potato, dropped into ice water, was proportional to the excess temperature, to its excess temperature over 32 degrees, the temperature of the ice water in Fahrenheit. The proportionality equation, well, the rate of temperature change, of course, we're talking implicitly about the time rate of temperature change, which is the d big T over d little t, change in temperature over change in time. And what's that equal to? Well, that's going to, or proportional to, that's going to be proportional to the excess temperature over 32. If the temperature is T, then the excess temperature over 32 is just the difference, T minus 32. And we have our proportionality constant K. This gives us a differential equation, and it turns out this differential equation will be easy to solve later on. But right now we're just trying to write proportionalities for rates of change, which are differential equations. Another one that seems to be pretty much true, the rate of depth change for a flow from a uniform cylinder out of a uniform hole is proportional to the square root of the depth. Now if we let y stand for the depth, as we have in our discussion so far, and let t stand for clock time, we see that the rate of depth change, again implicitly with respect to time, is dy dt, and that's proportional to the square root of the depth. The depth is y, so that's the square root of y, and we have our proportionality constant K once more. We have another one where if we imagine that we are moving away from a uniform point source of light, the illumination is going to decrease as we move away from that source. It turns out if we're moving at a constant speed that the rate at which illumination changes is inversely proportional to the clock time, assuming that we started at the position of the source and so forth. We're not going to worry too much about those assumptions right now, but that means that the rate of change of illumination, again with respect to clock time, is K times the reciprocal, or the inverse, of the clock time. That's what it means to be inversely proportional. Now there's a little bit of a difference between these two equations that you might want to note right now. Here we have dy dt, y being the dependent and t the independent variable, and on the right hand side we have a function of the dependent variable y. Here on the right side we have a function of the independent variable t. So that's this function is different in nature than this one. It turns out that that doesn't make a whole lot of difference when you're solving it. It depends more on the algebraic properties of these functions, whether it's easy to solve or not. But you can note that we could have either the independent or the dependent, dependent variable on the right hand side. We could even have both. So keep that in mind.